Okay, thank you, Roman. As Roman said, my name is Josh Hammerstein. I am the team lead for the Cyber Workforce Development Research Team here at the SEI. And today I'm going to be talking to you about cyber affordance visualization in augmented reality, or as we like to call it, caviar. So the main motivator behind this project is that despite the fact that cyberspace is defined as one of the 5 warfighting domains, it's really a new and novel domain for us, and we don't have a really solid, good grasp of how it can be leveraged at the tactical edge. When we think about cyberspace compared to those domains, air, land, sea, and space, those are physical domains. They occupy a physical space. They're tangible. They're distinctly separate from one another, yet we have a clear understanding of how they can be used to support one another, such as providing air support to ground troops. Cyberspace is different. It's abstract. It is not distinct from those domains. It's actually intertwined and interleaved with them. And so as a result, the question we ask ourselves is, how can we provide greater situational awareness to the warfighter about those intersections between cyberspace and those physical domains? So our approach to this problem is to use cyber affordances to visualize those intersections between cyberspace and these physical domains in order to provide the warfighter a greater understanding of cyber actions that they can take within their immediate geographic surroundings. When we talk about cyber affordances, what does that really mean? An affordance is defined as an opportunity that is presented by a physical object at the interface between an individual and the real world. So what it really is, it's some visual cue to perform some kind of action. So when we talk about cyber affordances, we're talking about using iconography to present potential cyber courses of action that a soldier could take within their immediate environment. But we need to be able to present these affordances in a way that it is unobtrusive to the warfighter and where they can easily take in the information, digest it, and incorporate it into their natural decision-making processes. And so as a result, what we've done is we're using augmented reality to present these affordances to the soldier and superimposing the cyber affordances on their natural field of view. So how might this work in a real-world scenario? So if we look at the top frame up there, we have some soldiers navigating through an urban area looking for a person of interest. They're just going to be using their standard operating procedures. There's nothing out of the ordinary of what they're doing here. Moving down into the second frame, now using Caviar, the soldiers have a cyber-enabled view. They can see the cyber terrain in their environment, but more importantly, they understand the potential cyber actions that they can now take. So as they look off into the distance, and it might be a little difficult to see in these slides, but there's a power substation down off in the distance, and they can see that there is a cyber effect that's available for temporarily disabling the industrial control systems that is tied to that power substation. If they look at one of the buildings down in the distance, they can see that there is a set of security cameras attached to the building, and again, there's a cyber effect available for monitoring those devices. And then looking at a more near-term building, a building closer in the distance, they can actually see a cyber affordance for that person that they're looking for. So as it turns out, that individual had a mobile device or a cell phone on them, and by using Caviar, Caviar was able to visualize an affordance for that device, and they're able to determine that that individual is in that building. So now that they have a greater understanding of the cyber terrain that's around them and the actions that they take, we move down to the final slide, where they can take in that information and determine what's the best course of action. Understanding that they have a cyber effect available that could give them a distinct tactical advantage using cyberspace. They call in that cyber effect to disable lighting in the area and then go into the building under the cover of darkness. So our initial work began using a Microsoft HoloLens as the augmented reality visor display and developing a custom Unity application for storing and then displaying these cyber affordances in one's field of view. The main goal of this initial work was to understand the challenges and limitations that we would encounter with this work. And what we discovered was there was two main challenges. One was that the HoloLens is really intended for indoor use. So we want this capability, obviously, to be used outside. And so we knew that there would have to be quite a bit of work that would have to be done in order to transition the HoloLens from indoor use to outdoor use. Secondly, and somewhat related, we recognized that the resources on the HoloLens were going to be limiting. Moving to an outdoor environment, the scenes were going to be much larger, and the computing resources that were available on the HoloLens visor just would not be sufficient. So what we did from there is we partnered with Dr. Steve Feiner at Columbia University. He's a subject matter expert in augmented reality. And he and his team within his computer graphics lab helped us address some of these issues and some of these problems. So with regards to using Caviar in an outdoor setting, what they did was they helped us incorporate real-time kinematic GNSS for outdoor use. And what that enabled us to do is to be able to display these cyber affordances on a person's field of view with centimeter level accuracy. The other big limitation with regards to the computing resources on the HoloLens, they addressed that by adding a gaming backpack to the system. The idea there was to offload the most intensive processing onto that gaming backpack, use it as a server, and then to feed the HoloLens headset with the scenes that were processed. The main artifacts out of this work, one were the hardware that you just saw, the Caviar hardware. In addition to that, we have the software architecture, including the Caviar server, which would runs on the backpack, and then the Caviar client application that runs on the HoloLens itself. We did have the opportunity to go down to Fort Gordon, Georgia, to conduct a focus group with about 20 soldiers from the Army 782nd MI Battalion. Taking a look at some of these findings a little bit more closely, the RF EM visualization. This was a particularly interesting finding because it wasn't the first time we had heard this. We had some discussions with a team here inside the SEI who was doing work with another government customer. This work involved placing sensors around a geographic area in order to monitor it. And one of the challenges of this work was finding an optimal sensor placement to get the best coverage out of these sensors. After talking with them about Caviar, they immediately recognized that if we could visualize the signal strength on these sensors, it would actually help solve this problem for that customer. Other issues, there was a lot of consensus about the visor. They felt that a visor might obstruct a soldier's field of view, potentially hinder their ability to maneuver, and they felt having a helmet-mounted device would be a better way to go since soldiers are already used to that using things such as night vision goggles. And then also there was also a lot of consensus about incorporating non-cyber uses into this Caviar system. So things like navigation, battle command, fires, and targeting. Looking at potential future work, so we identified some avenues where we could do additional work. One, the current setup is we need to reduce the hardware footprint. We added the gaming backpack there was a limitation that we had to address there. But at the end of the day, it's heavy, it's bulky, and we need to have a lighter footprint there. Similarly, now that we're using GNSS to have that centimeter level accuracy to display those cyber affordances on someone's field of view, we need a way to gracefully deal with the signal loss and potential signal degradation. There could be also other potential uses for Caviar if we can transition it to a mobile device. This work began before the Apple AR kit became available and became a thing. So being able to transition to a mobile device could open up avenues to other possible use cases. Instead of having a helmet-mounted device, now you could have a weapon-mounted device. And then lastly, addressing issues about ingesting data into Caviar and looking at things about what are the sources of information, where do we get them, how's that information curated. So with that concludes my presentation, and I'll field any questions if anybody has any. Okay. Yes, sir.
So you've got a size, weight, and power constraint. How many operations per second do you need to do? We've got some metrics on what we're going to be able to do with 14 nanometers. In terms of computation per watt, how much computation do you need?
I'll be honest, I don't know. So this work was undertaken by Dr. Steve Henderson, who started this work. He had since left the FBI, or the SEI, and not the FBI. He has since left the SEI. That was not a Freudian slip. So I'm more here, I'm able to kind of speak to the work at large as we get into the technical details. I can't speak to that, specifically. Anything else? Okay, thank you very much.